This is the most extreme scale-up the world has ever done. This is scale-up flops. Hopper is 1x, Blackwell 68x, Rubin is 900x. Scale-up flops. Every single layer of computing has been transformed. The amount of computation we need at this point as a result of agentic AI, as a result of reasoning, is easily 100 times more than we thought we needed this time last year. We made a fundamental transition in computer architecture. I just want you to know that, in fact, I've shown you a version of this about 3 years ago. It was called Grace Hopper, and the system was called Ranger. 3 years ago, we showed Ranger working, and it was way too large, but it was exactly the right idea. We were trying to solve scale up. Distributed computing is about using a whole lot of different computers working together to solve a very large problem. But there's no replacement for scaling up before you scale out. Both are important, but you want to scale up first before you scale out. And so the thing that we had to do was scale up first. Well, this is the way we scaled up. I'm not going to lift this. This is 70 pounds. This is the last generation system architecture. Is called HGX. This revolutionized computing as we know it. This revolutionized artificial intelligence. This is 8 GPUs. 8 GPUs. Each one of them is kind of like this. Okay, this is 2 GPUs, 2 Blackwell GPUs in one Blackwell package. And there are 8 of these underneath this. Okay? And this connects into what we call NVLink 8. This then connects to a CPU shelf like that. So there's dual CPUs, and that sits on top. And we connect it over PCI Express, and then many of these get connected with InfiniBand, which turns into what is an AI supercomputer. This is the way it was in the past. This is how we started. Well, this is as far as we scaled up before we scaled out. But we wanted to scale up even further. And so we had to do something quite remarkable, re-engineer how NVLink worked and how scale-up worked. And so the first thing that we did was we said, listen, the NVLink switches are in this system embedded on the motherboard. We need to disaggregate the NVLink system and take it out. So this is the NVLink system. Okay, this is an NVLink switch. This is the highest performance switch the world's ever made. And this makes it possible for every GPU to talk to every GPU at exactly the same time at full bandwidth. Okay, so this is the NVLink switch. We disaggregated it, we took it out, and we put it in the center of the chassis. So there are 18 of these switches in 9 different racks, 9 different switch trays, we call them. And then the switches are disaggregated. The compute is now sitting in here. This is equivalent to these 2 things in compute. What's amazing is this is completely liquid cooled. And by liquid cooling it, we can compress all of these compute nodes into one rack. This is the big change of the entire industry. All of you in the audience, I know how many of you are here. I want to thank you for making this fundamental shift from integrated NVLink to disaggregated NVLink, from air-cooled to liquid-cooled, from 60,000 components per computer or so to 600,000 components per rack, 120 kilowatts, fully liquid-cooled, and as a result, we have a 1 exaflops computer in one rack. Isn't it incredible? So this is the compute node. This is the compute node, okay? And that now fits in one of these. 20 cars worth of parts and integrates into one supercomputer. Well, our goal is to do this. Our goal is to do scale up. And this is what it now looks like. We essentially wanted to build this chip. It's just that no reticle limits can do this. No process technology can do this. It's 130 trillion transistors. 20 trillion of it is used for computing. So it's not like you can't reasonably build this anytime soon. And so the way to solve this problem is to disaggregate it, as I described, into the Grace Blackwell NVLink 72 rack. But as a result, we have done the ultimate scale-up. This is the most extreme scale-up the world has ever done. The amount of computation that's possible here, the memory bandwidth, 570 terabytes per second. Everything in this machine is now in T's. Everything's a trillion. And you have an exaflops, which is 1,000,000 trillion floating point operations per second. Okay, just to put it in perspective, this is what a 100 megawatt factory looks like. This is a 100 megawatt factory. You have, based on Hoppers, you have 45,000 dies, 1,400 racks, and it produces 300 million tokens per second, okay? And then this is what it looks like with Blackwell. You have 86, yeah, I know. That doesn't make any sense. I want to show you now what an AI factory looks like, but AI factories are so complicated. I just gave you an example of one rack. It has 600,000 parts. And now, in the second half of this year, we'll easily transition into the upgrade. So we have the Blackwell Ultra NVLink 72. It's 1.5 times more flops. It's got a new instruction for attention. It's 1.5 times more memory. All that memory is useful for things like KV cache. It's 2 times more bandwidth, okay, for networking bandwidth. And so now that we have the same architecture, we'll just kind of gracefully glide into that, and that's called Blackwell Ultra, okay? So that's coming second half of this year. Look, we're building AI factories and AI infrastructure. It's going to take years of planning, which is the reason why I show you our roadmap a couple, 2-3 years in advance. And so we plan this out in multiple years. The next click, 1 year out, is named after an astronomer, and her grandkids are here. Her name is Vera Rubin. She discovered dark matter. Vera Rubin is incredible because the CPU is new. It's twice the performance of Grace, and more memory, more bandwidth, and yet just a little tiny 50-watt CPU is really quite incredible. Okay? And Rubin, brand new GPU, CX9, brand new networking smart NIC, NVLink 6, brand new NVLink, brand new memories, HBM4. Basically, everything is brand new except for the chassis. And this way, we could take a whole lot of risk in one direction and not risk a whole bunch of other things related to the infrastructure. And so Vera Rubin, NVLink 144, is the second half of next year. Now, one of the things that I made a mistake on, and so I just need you to make this pivot, Blackwell is really 2 GPUs in one Blackwell chip. We call that one chip a GPU, and that was wrong. And the reason for that is it screws up all the NVLink nomenclature and things like that. So going forward, without going back to Blackwell to fix it, going forward, when I say NVLink 144, it just means that it's connected to 144 GPUs. And each one of those GPUs is a GPU die, and it could be assembled in some package. How it's assembled could change from time to time, okay? And so each GPU die is a GPU. Each NVLink is connected to the GPU. And so Vera Rubin NVLink 144. And then this now sets the stage for the second half of the year, the following year, we call Rubin Ultra. So this is Vera Rubin Ultra, second half of 27. It's NVLink 576, extreme scale up. Each rack is 600 kilowatts, 2.5 million parts, okay? And obviously a whole lot of GPUs. And everything is X factor more. So 14 times more more flops, 15 exaflops. Instead of 1 exaflop, as I mentioned earlier, is now 15 exaflops, scaled up exaflops, okay? And it's 4.6 petabytes, so 4,600 terabytes per second scale up bandwidth. I don't mean aggregate, I mean scale up bandwidth. And of course, a brand new NVLink switch and CX9, okay? And so notice 16 sites, 4 GPUs in one package, extremely large NVLink. Now just put that in perspective. This is what it looks like, okay? Now this is going to be fun. So you are just literally ramping up Grace Blackwell at the moment, and I don't mean to make it look like a laptop, but here we go. Okay, so this is what Grace Blackwell looks like, and this is what Rubin looks like. ISO dimension. And so this is another way of saying, before you scale out, you have to scale up. Does that make sense? Before you scale out, you scale up. And then after that, you scale out with amazing technology that I'll show you in just a second. All right, so first you scale up, and then now that gives you a sense of the pace at which we're moving. This is the amount of scale up flops. This is scale up flops. Hopper is 1x, Blackwell 68x, Rubin is 900x. Scale up flops. Okay, how do we scale up? Well, we were preparing to scale out. That was scale up, was NVLink. Our scale out network is InfiniBand and Spectrum-X. Most were quite surprised that we came into the Ethernet world. And the reason why we decided to do Ethernet is if we could help Ethernet become like InfiniBand, have the qualities of InfiniBand, then the network itself would be a lot easier for everybody to use and manage. And during Rubin's time frame, we would like to scale out the number of GPUs to many hundreds of thousands. Now, the challenge with scaling out GPUs to many hundreds of thousands is the connection of the scale out. This connection on scale up is copper. We should use copper as far as we can, and that's, call it a meter or two. And that's incredibly good connectivity, very high reliability, very good energy efficiency, very low cost. And so we use copper as much as we can on scale up, but on scale out, where the data centers are now the size of the stadium, we're going to need something much long distance running. And that's where silicon photonics comes in. The challenge of silicon photonics has been that the transceivers consume a lot of energy. So first of all, we're announcing NVIDIA's first co-packaged option, silicon photonics system. It is the world's first 1.6 terabit per second CPO. It is based on a technology called micro-ring resonator modulator, and it is completely built with this incredible process technology at TSMC that we've been working with for some time. This is an example of a transceiver. They did a very good job tangling this up for me. Okay. This is where you got to turn reasoning on. All right, so this one right here, this is 30 watts, just so keep you remember, this is 30 watts. And if you buy it in high volume, it's $1,000. This is a plug. On this side is electrical, on this side is optical. If we had 100,000 GPUs, we would have 100,000 of this side, and then another 100,000, which connects the switch to a switch, and then on the other side, I'll attribute that to the other NIC. If we had 250,000, we'll add another layer of switches, and so each GPU, every GPU, 250,000, every GPU would have 6 transceivers. Every GPU would have 6 of these plugs, and these 6 plugs would add 180 watts per GPU, 180 watts per GPU, and $6,000 per GPU, okay? And so the question is, how do we scale up now to millions of GPUs? Because if we had 1 million GPUs, multiplied by 6, right, it would be 6 million transceivers times 30 watts, 180 megawatts of transceivers. They didn't do any math, they just moved signals around. And so the question is, how could we afford, and as I mentioned earlier, energy is our most important commodity. Everything is related ultimately to energy. So this is gonna limit our revenues, our customers' revenues, by subtracting out 180 megawatts of power. And so this is the amazing thing that we did. We invented the world's first MRM micromirror, and this is what it looks like. There's a little waveguide, you see that on that waveguide, goes to a ring. That ring resonates, and it controls the amount of reflectivity of the waveguide as it goes around, and it limits and modulates the energy, the amount of light that goes through. And it shuts it off by absorbing it or pass it on. Okay, it turns the light, this direct continuous laser beam, into ones and zeros. And that's the miracle. And that technology is then, that photonic IC is stacked with the electronic IC, which is then stacked with a whole bunch of micro lenses, which is stacked with this thing called fiber array. These things are all manufactured using this technology at TSMC they call it COUPE, and packaged using a 3D CoWoS technology, working with all of these technology providers, a whole bunch of them, the names I just showed you earlier, and it turns it into this incredible machine. Just a technology marvel. And they turn into these switches. Our InfiniBand switch, the silicon is working fantastically. Second half of this year, we will ship the silicon photonics switch in the second half of this year. In the second half of next year, we'll ship the Spectrum X. Because of the MRM choice, because of the incredible technology risks that over the last 5 years that we did, and filed hundreds of patents, and we've licensed it to our partners so that we can all build them. Now, we're in a position to put silicon photonics with co-packaged options, no transceivers, fiber, direct fiber into our switches with a radix of 512. This is the 512 ports. This would just simply not be possible any other way. And so this now set us up to be able to scale up to these multi-100,000 GPUs and multi-million GPUs. And the benefit, just so you imagine this is incredible. In a data center, we could save, let's say 60 megawatts. 6 megawatts is 10 Rubin Ultra racks. 6 megawatts is 10 Rubin Ultra racks, right? And 60, that's a lot. 100 Rubin Ultra racks of power that we can now deploy into Rubins. All right, so this is our roadmap. Once a year, an architecture every 2 years, a new product line every single year, X factors up, and we try to take silicon risk or networking risk or system chassis risk in pieces so that we can move the industry forward as we pursue these incredible technology. Our next generation will be named after Feynman. Okay, NVIDIA's roadmap. Let me talk to you about enterprise computing. AI and machine learning has reinvented the entire computing stack. The processor is different, the operating system is different, the applications on top are different. And so we need a new line of computers. This is what a PC should look like. 20 petaflops. Unbelievable, 72 CPU cores, chip-to-chip interface, HBM memory, and just in case, some PCI Express slots for your GeForce. Okay, so this is called DGX Station. DGX Spark and DGX Station are going to be available by all of the OEMs. HP, Dell, Lenovo, Asus. It's going to be manufactured for data scientists and researchers all over the world. This is the computer of the age of AI. This is what computers should look like. And this is what computers will run in the future. And we have a whole lineup for enterprise now, from little tiny one to workstation ones, the server ones, to supercomputer ones, and these will be available by all of our partners. So next, let's go somewhere else. Let's go talk about robotics, shall we? Let's talk about robots. There are all kinds of robotic systems. Your infrastructure will be robotic. Billions of cameras in warehouses and factories, 10, 20 million factories around the world. Every car is already a robot, as I mentioned earlier, and then now we're building general robots. Everybody pay attention to this space. This could very well likely be the largest industry of all. At its core, we have the same challenges. As I mentioned before, there are three that we focus on. They are rather systematic. One, how do you solve the data problem? How, where do you create the data necessary to train the AI? Two, what's the model architecture? And then three, what's the scaling laws? How can we scale either the data, the compute, or both, so that we can make AIs smarter and smarter and smarter? How do we scale? And those fundamental problems exist in robotics as well. In robotics, we created a system called Omniverse. It's our operating system for physical AIs. You've heard me talk about Omniverse for a long time. We added two technologies to it. Today I'm going to show you two things. One of them is so that we could scale AI with generative capabilities. A generative model that understands the physical world. We call it Cosmos. Using Omniverse to condition Cosmos, and using Cosmos to generate an infinite number of environments allows us to create data that is grounded, controlled by us, and yet be systematically infinite at the same time. Okay, so you see Omniverse, we use candy colors to give you an example of us controlling the robot in the scenario perfectly, and yet Cosmos can create all these virtual environments. The second thing, just as we were talking about earlier, one of the incredible scaling capabilities of language models today is reinforcement learning, verifiable rewards. The question is, what's the verifiable rewards in robotics? And as we know very well, it's the laws of physics. Verifiable physics rewards. And so we need an incredible physics engine. Well, most physics engines have been designed for a variety of reasons. They could be designed because we want to use it for large machineries, or maybe we design it for virtual worlds, video games and such. But we need a physics engine that is designed for very fine-grained, rigid and soft bodies, designed for being able to train tactile feedback and fine motor skills and actuator controls. We need it to be GPU accelerated so that these virtual worlds could live in super linear time, super real time, and train these AI models incredibly fast. Can you imagine just now what you were looking at is complete real-time simulation? This is how we're going to train robots in the future. Just so you know, Blue has two computers, two NVIDIA computers inside. Look how smart you are. Yes, you're smart. Okay. All right. Hey, Blue, listen. How about let's take them home? Let's finish this keynote. It's lunchtime. Let's wrap up. I want to thank all of you for coming to GTC. We talked about several things. One, Blackwell is in full production, and the ramp is incredible. Customer demand is incredible, and for good reason. Because there's an inflection point in AI, the amount of computation we have to do in AI is so much greater as a result of reasoning AI and the training of reasoning AI systems and agentic systems. Second, Blackwell NVLink 72 with Dynamo is 40 times the performance, AI factory performance of Hopper. And inference is going to be one of the most important workloads in the next decade as we scale out AI. Third, we have an annual rhythm of roadmaps that has been laid out for you so that you could plan your AI infrastructure. And then we have three AI infrastructures we're building. AI infrastructure for the cloud, AI infrastructure for enterprise, and AI infrastructure for robots. Have a great GTC. Thank you. Hey, Blue. Let's go home.